doing a breakout room. That way things can be a little bit more collaborative. But right now, let's just do the warm-up, which is some oxidation numbers. Okay, cool. Hi, Fabiola. It's nice to see you. Nice to see everybody. So we just have a quick warm-up starting out with find the oxidation numbers for H2CO3 and zinc hydroxide. So just for the sake of time, I'm going to be going through this warm-up. So for H2CO3, we know that we have a neutral charge for the entirety of the compound. So the total charge is 0. So I'm going to set the whole thing equal to 0. And then we know that H has a +1 charge. And then that's going to be times 2. We have 1C, and we have 3 times -2. Because we know that oxygen has an oxidation number of -2 at all times, except for hydrogen peroxide. So when we simplify this out, we get 2 plus C minus 6 equals 0. So we get C equals -6, or +6 minus 2, which is equal to 4. So that is the oxidation number for carbon. Something to keep in mind when you're doing oxidation numbers is when you're looking for oxidation numbers, just keep in mind the polyatomic ions and how things balance out between different compounds and elements, just in case the charge isn't necessarily given. And then for the second problem we have zinc. We're looking for zinc. So we have a hydroxide, so we have 4 O's and 4 H's, and the total charge is -2. So we have -2 equals 4 times -2 plus 4 times +1 plus Zn. So this is for oxygen. This is for hydrogen. Okay. So then you have -8 plus 4 equals -2. So I'm going to add 8 on both sides and subtract 4 on both sides. So I have Zn minus, or -2 minus 8 is +6, and then -4 equals Zn. A little preparation in there, but don't worry about that yet. I'm going to start going through the problem. So in terms of our first step, let me reopen the chat, that way I can just look at it. Okay. So in terms of the first step, we have to put this entire reaction into 2 half reactions. So I'm going to split it by HCOOH with CO2. So I'm going to say HCOOH goes to CO2. And then I'm going to split it also between MnO4 minus with Mn plus 2. Okay. So the first thing that we're going to do is we're going to look at the individual elements that aren't hydrogen or oxygen, and we're going to balance them on both sides. Considering both of our half reactions, it looks like we have an equal number of carbons on both sides, and then we also have an equal number of manganese on both sides of the half reactions. So then what's the next step? The next step is to balance the oxygens. If I look at the first half reaction, I'm going to call this equation 1. Oh, okay. Let's move that. I'm going to call this equation 1, and I'm going to call this equation 2. It looks like equation 1 has the same number of oxygens on either side. However, in equation number 2, we have 4 oxygens and 0 on the product side. So I'm going to add 4 H2O. just to balance out the oxygens. So let me do this. Equation 1 and equation 2. Okay. So now that I've balanced the oxygens, I'm going to start balancing out the hydrogens. Looking at, oh, thanks, Dylan. Looking at the first equation, it looks like we have 2 hydrogens on the product, or the reactant side of the equation, and then we have 0 on the product side. So I'm going to add 2H plus. So, and then it's the opposite for equation number 2, right? We have 8 hydrogens on the product side, so I'm going to add 8H plus on the reactant side. So now that I've done that, I've balanced out the oxygens, I've balanced out the hydrogens, and I've balanced out the individual elements. Now I just need to balance out the charges on both the product and reactant side. So I'm going to do this by calculating the charges on both sides. So for equation 1, HCOOH has a neutral charge, so it's 0 on this side. CO2 plus 2H plus has a positive 2 charge on this side. So I'm going to add 2 electrons to match it up with the 0 on the other side. So plus 2E minus. As for the other side, as for equation number 2, it looks like I have 8H plus a minus, or plus negative 1. So I have a total charge of 7 plus. And then on the other side, I have a total charge of 2 plus. And plus 2. 2 plus 2, both are the same. So in order to make this have an equal charge to the reactant side, I'm going to add 5 electrons, 5E minus, on the reactant side of this equation. Let me just go out just a little bit. Alrighty. So now that I have all the charges are balanced, oxygen's balanced, hydrogen is balanced, individual elements are balanced, all I need to do is multiply each equation by some value that makes the number of electrons on either of these equations the same. So what I'm going to do is I'm going to multiply equation number 1 by 5 and equation number 2 by 2. So that way, for equation 1, I'm going to continue equation 1 down here. I get 5HCOOH goes to 5CO2 plus 10H plus 10E minus. And then equation 2, I get 10E minus plus 16H plus 2MnO4 minus goes to 2Mn plus 2 plus 8H2O. So all I have to do is combine equations 1 and 2 and then cancel out any spectator elements. So what do I mean by spectator elements? I mean elements that are same on both the product side and the reactant side of the equation. So I'm going to combine these two. So I'm going to start with the reactants. So I have 5HCOOH plus 10E minus plus 16H plus 2MnO4 minus, and then I'm going to include the little arrow right here, and I'm going to split it. And then the product side, I have 5CO2 plus 10H plus 10E minus plus 2Mn plus 2 plus 8H2O. So then all I have to do is cancel out the things that are the same. So I have 10 H plus on the product side and 16 on the reactant side. So I can get rid of this one. This one can just be gone, be out of here. And then this one becomes 8 H plus. The electrons cancel out, which is a good sign. If your electrons don't cancel out, then that means you have to try and rebalance it so that way that they do. And then I don't think I see anything else that needs to be canceled out. So my total equation, or my balanced redox reaction, should be 5HCOOH plus 2MnO4 goes to, I'm going to continue down here, 5CO2 plus 2Mn plus 2 plus 8 water. And that looks like a lot of other people got the exact same thing. In fact, it looks like everybody who answered got the same thing. So great, awesome. We're all on the same page. That's awesome. Are there any questions? Alrighty. So I have some answers right here on the OneNote. So I'm going to explain the first two really quick. So let me just stop sharing so that way I can show you and you guys can see it much more easily. So I have my periodic table right here. And as you can see, I've labeled the different orbitals and stuff. So something that I've done on the side right here is I have 1 through 7. This is, these are the energy levels for the s orbital. And then inside here I have 3 through 6. These are the energy levels for the d orbital. And then here, okay, here should be 2 through 6. And that should be for the p orbital. And then down here, the lanthanides, this is all the f orbital. And then you only have 4 and 5 energy level, or is it 6? I think it's 4, 5, or 6, or 7. And the way you go about finding quantum numbers is you go by the actual values that are on the periodic table. So for instance, I have 1s. So like, let's say I'm looking for hydrogen. The quantum number I would get is 1s1. That's all I would get. If I were looking for helium, I would get 1s2 for my quantum numbers. If I were looking for, let's see, if I were looking for beryllium, I would get 1s2, 2s2. If I were looking for boron, it would be 1s2, 2s2, 2p1. I hope that explains quantum numbers a little bit better. However, I'm going to go back to sharing my screen. And that's how I got the first two values for my quantum numbers, is I used that long method by going 1s2, 2s2, 2p6. And then I did the same thing for germanium, all the way up to 4p2. And then for lead, because I didn't want to go through all the hassle of writing out this long list of quantum numbers, instead, what I did, stop sharing one more time, a shortcut is to use the noble gases, everything from helium to radon. It's kind of hard to point when you're doing it inversely. So everything from helium to radon, you can use it as like an abbreviation, and then you just continue with the quantum numbers as you go. So let's go back to the shared screen. Okay, so that's what I did for lead. The element that is right above lead, or the noble gas that's right above lead, is xenon. So I did xenon in brackets, 6s2, 5d10, 6p2. Now, what Fabiola and you guys were doing a second ago was you guys were finding the actual numbers, like the energy level, the n values, the L values, the M value, and the spin. So for neon, what that's going to look like is you're going to use this last orbital that the electron comes from. So the energy level is going to be the number in front of everything. So that's going to be 2, is going to be N. For L, it's going to be the orbital type. So if you remembered, we have S, P, D, and F. This is 0, this is 1, 2, and 3. Since we have P, the the L value is equal to 1. For our M value, it's going to be the position on the orbital. So the P orbital has 3 spaces. So you have 1, 2, 3, 0, 1, negative 1. And that's how you label the positions. When you go with the S orbital, so let me do the S orbital real quick. So this is the P orbital. The D orbital looks like this: 1, 2, 3, 4, 5. And you have 0, 1, 2, minus 1, minus 2. And F has 7 spaces. So you have 1, 2, 3, 4, 5, 6, 7. You have 0, 1, 2, 3, minus 1, minus 2, minus 3. So that's what you get for your orbitals. Since our case, we're looking at the P orbital, and we have how many? We have sp6. This is the way you fill out the electrons, is you do it with arrows, and you start with the upward facing arrows, and you just do 1 in every slot. So I'll show you. So you do positive arrow, positive arrow, positive arrow. That's 3 electrons. And then you do negative arrow, negative arrow, negative arrow. So our position, our last electron is this downward facing arrow. So that's in position 1. So our M value is 1. And now for the spin, Fabiola was explaining this just a moment ago. Spin depends on is just the orientation, is how it's spinning. So spin, since the arrow is facing down, we call it -1/2. And that's how you get the quantum numbers. And that's how you do it based off of the actual name of the quantum numbers. So are there any questions regarding quantum numbers now that we've gone through this? Feel free to use the chat. Oof. Okay. Oh boy. Okay. Can you do number 4? Yeah, sure. Let's see. Just really quick. So I'm going to use the abbreviated format. So LU, where's that? Okay. So the value I'm going to use is radon, so Rn. So I have the brackets. So I start with 7s2, 6d10, or sorry, this is 6f. Oh boy, come on. Okay, this is 6. This is more than one equation. So I'm looking for the position. I'm looking for delta x. All I'm given is the nanometers, the wavelength, and the mass. Thankfully, I have an equation that has both the wavelength and the mass. And I have another equation that has both mass and velocity involved, along with position. The only thing I don't have as of now is velocity. Luckily, this equation only has lambda, mass, and Planck's constant, which we already know. Planck's constant, just for a reminder, is 6.626 times 10 to the negative 34. And I'm not going to be so worried about units for this instance because Planck's constants does not usually, like, it's not used in different units, so there's no need to worry about the units. So what I'm going to do is I'm going to plug in my value for wavelength into here. And I'm going to plug in my value for the mass of an electron right here. And I'm going to solve for V. However, what I like to do is I like to solve for V first and then plug everything in. So V equals what? We have lambda, we have H over M lambda. That's our V. So that's going to be 6.626 times 10 to the negative 34 over 9.109 times 10 to the negative 31 kilograms, which is our mass of the electron. And then we have the wavelength, which is 900 times 10 to the negative 9 meters. That's just a little trick I like to do when I'm working with nanometers as opposed to meters. I just take the number and multiply it by 10 to the negative 9. So the value for velocity I should get so the value for velocity I should get is 808.236 meters per second. That's the value I should get for velocity. And then once I've found velocity, I can plug it into my equation here. So I have delta x times 9.109 times 10 to the negative 31 kilograms times 808.236 meters per second is equal to or greater than Planck's constant over 4 pi. So delta x is equal to Planck's constant over 4 pi times 1 over 9.109 times 10 to the negative 31 times 808 meters per second. So then the value I should get for the change in position So the value that I should get for delta x is 7.0685 times 10 to the negative 7. And this should probably be in meters. That's what I get for my delta x. That's my final answer there. Okay. Let me just leave it on there for a second. Okay. All right, for part 2, given the velocity of the electron from the last problem, find the frequency of the electron. There's another equation that I think actually that you guys don't have, but even if you didn't have this equation, you could still solve it. So the equation that I'm referring to is F, or frequency. So I'm going to say frequency is F in this case. is equal to CV. That's what I'm referring to. If you don't have this equation, and honestly you don't even need it even for this problem, you could use C equals F or V lambda or F lambda. You could use either of these equations. You could use the velocity that you found, or you could use the frequency. And I'll just do both just to make y'all feel better. Just so that way you don't feel like you have to use one thing or the other. So F equals, so that's 3 times 10 to the 8 for the speed of light, times the velocity that we got. So I should get 2.424 times 10 to the 11, and that's 1/seconds. So for frequency, I should get F equals C over lambda. So again, 3 times 10 to the 8 over 900